Okay, we're continuing on here, chapter 19, I think. So we talked about last time kind of transition metals and a little bit about some characteristics of transition metals and some trends and all that fun review stuff. But really, we talked about transition metals because as we're going into the rest of this chapter here, we are going to talk about complex ions. And a lot of complex ions basically will have transition metals sort of in the center of them. And as we talked about, again, some of the important things, definitely in terms of complex ions and things of that nature are, again, electron configuration. Remember that the transition metals will always lose their s electrons first when they do gain a charge. And then if necessary, they will go into the d electrons to take out the rest of them that's needed. So let us get into really the heart of this chapter, which is coordination compounds and really complex ions. So a coordination compound is really consisting of two things. It consists of a complex ion, and it consists basically of a counter ion. So you can kind of think of a coordination compound as pretty much like an ionic compound. It's got really a positive guy and it's got a negative guy. So a coordination compound will have an ions that will be positively charged, and it will have some ions that will be negatively charged, and they'll come together to form a coordination compound. A complex ion, as we've seen a couple of times before and earlier on when we were talking about KF and even this morning, is basically a metal cation in the center. Again, a lot of times a transition metal that's got a kind of large positive type charge, and it has one or more either molecules or ions that are bound to it. Those molecules or ions are what are referred to as ligands. So since the metal in the middle basically has a positive charge, as we talked about, it is sort of acting as a Lewis acid, which means it really is electron deficient. So that's why it has obviously a positive charge, because it's lost electrons. And really our ligands are, as we've seen, Lewis, spit those up, bases. So they are Lewis bases. And Lewis bases are guys that have a pair of electrons that will donate. So remember, a little bit different than sort of Bronsted-Lowry definition, dealing with electrons when we're dealing with our Lewis guys here. So a Lewis base is something that can donate a pair of electrons. A Lewis acid will accept basically a pair of electrons. And that's sort of the way that coordination compounds come together, almost in a Lewis acid base type situation, where we have these electrons being donated and the electrons being accepted. In order for something to be a ligand, it needs to have at least one unshared pair of valence electrons. So usually things that are polar, that has some non-bonding electrons on a sort of electronegative type atom, are really good ones. So water here obviously has the electrons. Ammonia, which is a really good ligand, which you use today to complex out the copper in the experiment. Anything that's really an ion with a negative charge, in order for it to become negatively charged, it had to gain electrons, which means it has some extra electrons to sort of donate. So those guys are also really, really good. In this case here, this guy has 6 different ligands attached to it. And again, the attachment here from the nitrogen would obviously come from the nitrogen that has those lone pairs. And obviously here the chloride would attach there as well. Now, when we talk about the complex ion and the counter ion, we can really have either scenario. And what I mean by that is you could have a positive counter ion to a negative complex ion, or you could have the complex ion part being positive overall, and you could have a negative counter ion that will balance it out. So both the complex ion can either be positive or negative, and the counter ion will also be positive or negative, obviously to balance out the charge there. So a coordination compound will pretty much have no overall charge, much like an ionic compound. Um, and so everything sort of balances out to zero in that sense. Any questions on that there? Now, when we have the donor atom and how many ligands are attached, that is what is sometimes referred to as a coordination number. Now, it's important when we talk about coordination number, it is not necessarily how many of ligands there are, but it is actually based on how many times the ligand will bind to the central atom. So it really is how many atoms are directly attached to the central atom. And there are some different ligands. For example, here, ammonia and water, they are what are referred to as being monodentate or unidentate. And basically what that means is they will only bind to a metal with one atom. So in the case of the nitrogen here, it will only bind to the metal. In the case of the oxygen, it is the only atom there that will bind to the metal. But not all ligands are like that. There are certain ligands that have the ability to bind in more than one spot. And those are referred to, for example, as bidentate. These are guys that can bind basically in two spots per atom. Ethyl endyl diamine is a prime example and a very common example of a bidentate ligand that we see a lot. It also is abbreviated with an EN. So if you see kind of parentheses EN, it is talking about ethyl endyl diamine, which, you know, if I remembered chemistry, I would remember what that looks like. But it looks something like a little bit of this action here. So in this particular case, it is the nitrogens here. And this is one molecule of ethyl endyl diamine. Put it back in. I drew it underneath. That worked. And for every one of those EN molecules, you can actually get two things binding in per atom. So you kind of get like a 2-for-1 on the coordination number. So if we had one ethyl endyl diamine as the ligand only, the coordination number would be 2, not 1. So it would be 2 in this case because everyone gives you 2. Another very common bidentate one that does pop up a lot is C2O42-. That is oxalate. And if you draw up some oxalate here, looks something like this. A little double bond action, a little single bonded action. And it is these badly drawn single bonded oxygens here that can basically bind to the metal. So for every one of oxalate, you also get basically 2 atoms that will bind per molecule. So again, in terms of the coordination number, for every oxalate that you have is basically 2 for the coordination number. There's also some that could bind in a ton of different places, and that's ethyl endyl diamine tetraacetic acid, which is EDTA, and that actually can bind 6 places per every one of those molecules. So that's a really good sort of metal chelator, it's called. It basically grabs up a metal in 6 places per molecule, so it pretty much surrounds the metal in that case. So what happens is sometimes people, when they see, say, a formula, you know, they'll go, hey, I got a metal and, you know, I got like Cl 4 or something like that. And they'll go to coordination numbers 4, and then they look at another one and go, all right, I got 2, and they'll go the coordination numbers 2. And again, in this case, it would not, the coordination number here would actually be 4 because each of these could bind in 2 places. So it's not always the little subscript next to the ligands in the formula will give you the coordination number. It will if they are monodentate, but if they're bidentate or polydentate, then you have to kind of take that into account. Now, how do we know how many sort of ligands usually will attach? It kind of depends on the charge that we see for the metal. So typically speaking, guys with +1s, usually 2 ligands will attach there, occasionally 4. When we get into the +2s, that's really where we see a lot of 4s and 6s sort of come in. And then when we get into +3s, that's where we see basically 6 sort of ligands attach in there, except for gold, they will kind of do 4. And again, if you think about it, sort of the greater the positive charge, greater the electron deficiency. So it's going to allow for more acceptance of electrons and going to allow more guys to basically come in as Lewis bases. So that is a drew it right. So that's good. So that is EN there, which is ethylenediamine. To the right there is EDTA, and it will attach, as I mentioned, this is one, by the way, that was one molecule of EDTA, this entire thing. And basically it's attached in 1 place, 2 places, 3 places, 4 places, 5 places, and 6 places. So it can really, really surround a metal. And again, that's what is sometimes referred to as a chelating agent. A lot of times they'll add things like EDTA to all kinds of stuff to sort of trap out any metals that might come along for the ride. If you look at ingredient labels on all kinds of things like shampoos and other things like that, you'll see like EDTA kind of listed as part of it as well to sort of grab out a lot of those things. So bidentate and polydentate guys are sometimes referred to as chelating agents because they really can grab out. This is a table, and you have a similar one in your book of some common monodentate, bidentate, and polydentate ligands. Again, these are some of the very common ones that we see a lot: water, ammonia, cyanide, nitrite, hydroxide, thiocyanates, and really any of those halogens there, which are known as halides when they have a negative charge. There's our oxalate that I mentioned before. And there's also our EN. By the way, the EN is used both in formulas, a lot of times, and very commonly in naming as well. So don't be surprised you kind of see that EN in kind of both places. It's very commonly used. This is diene, which actually binds in 3 places at each of those nitrogens. Basically, it's able to bind. And like I said before, this is the big EDTA, which, by the way, has a -1, -2, -3, and -4 charge overall. And it can coordinate and basically bind in at 6 places. So let's take a look at a couple of things here. And first thing is, these are both coordination compounds. And usually there is sort of a pattern as to how these things are written. Usually when you look at a coordination compound, the guy in the bracket is usually your complex ion. And then obviously the guy outside of the bracket is usually your counter ion. So with that being said, why don't you figure out the oxidation numbers for the metals that are in the complex ion part. So take a moment and figure out what is the oxidation numbers for the metals and each of those complex ions that are part there. So once again, and when we look at this, here would be our complex ion part. This then would be our counter ion. So what we would do here is kind of like normal. We would start with OH, which is hydroxide. So that is a -1, and there's 4 of them, which means that's a -4. The potassium is +1. That means here the gold would be a +3 oxidation state. So the gold here would have a +3 oxidation state. Any question on that one there? Same thing on this side here. This would be our complex ion part that's in the brackets. That means that in this case, it is the nitrate that is our counter ion. Once again, we start with ammonia, which has no charge, so it's 0. Nitrate is -1, and there's 3 of them, which gives you a -3. So to balance that out here, the chromium would also, in this case, be carrying a +3 charge. Any questions on how to identify the oxidation numbers here? So in this particular case, a couple things. The coordination number for this guy would be what? Coordination number would be 4. There are 4 hydroxides attached to the metal, the gold. Each hydroxide is monodentate, which means it only binds in one place. So the coordination number would be 4. Coordination number on this side would be, it would be 6. There are 6 ammonias that are directly attached to the chromium. Each ammonia is also monodentate, so it'll bind through the nitrogen. So the coordination number here would be 6 to the guy to the right. Now, in the case to the guy on the left there, coordination compounds are always written very much like ionic compounds, which means it is always the positive guy first and then the negative guy, both in names and formulas. So just like you do in ionic compounds. That means in this particular case, our counter ion is actually positive and our complex ion is negative. And we know that basically based on the arrangement. So what we know is in this particular case, if we pulled out just the complex ion part, what would be the overall charge on the complex ion part? It would be, I think you said -1, and it would be because once again, this is -1 and there's 4 of them. We now know that the gold is +3, which means the overall charge here, the complex ion part actually is -1. And that is why we only have 1 potassium there to balance it out, because potassium is +1. So +1 and -1 gives us 0 when we put it together to make our coordination compound. Again, very similar to what you do with ionic compounds in this case. Any questions on that there? We actually have the opposite happening over here on the right-hand side. Our complex ion is actually positive because it comes first, and our nitrate's negative because it comes second in terms of our counter ion. In this case, if we pulled out just the complex ion, the overall charge on just the complex ion part here, this guy once again is 0. As we figured out, that is +3, which means we have a +3 charge overall for just the complex ion part. That is why in this case, we don't have just 1 nitrate, but we have 3 of them. That is so that all 3 of them will give us a -3 charge to balance out the +3 charge that we see there for our complex ion. So you obviously could have more than 1 counter ion, however many you need to balance out the overall coordination compound to 0. Any questions on that there? Okay. And you'll be able to name these guys in just a second. Yes. So let's talk about how we would go about naming these things, because you thought all your naming days were over, but a few more things to name. So to name coordination compounds, as I mentioned a second ago, the cation or the positive guy comes first, then the negative guy. That again goes for both the name and the formula. Within the complex ion, you name the ligands first, and you put them in alphabetical order, regardless of a prefix that may be there. So whatever the kind of first initial there of the, or letter of the name is what you go by. Now, names of anionic ligands end with the letter O. Neutral guys are usually called by their name, but there are some exceptions, like water is called aqua or aqua, depending on your book. CO is carbonyl, NH3 is amine. When there are multiple ligands of the same type, like we saw earlier, there's like 2 Cls and like 4 NH3s. We do use Greek prefixes. So we use di for 2, tri for 3, penta for 5, tetra for 4, I skipped, and hexa for 6. Now, if there is a ligand that actually already contains a prefix in it, then we roll with some other prefixes like bis, tris, tetrachus for 4. What comes to mind is en. That's endyl ethyl diamine. So that guy actually has the di as part of its name. So if you had more than one of those guys, you would use like, so for example, if you had 2 of these guys, you would use bis, endyl ethyl diamine, because it already has the di in its name. The oxidation number of a metal is written in Roman numerals, and it always follows the metal name. And we do use Roman numerals for these type of guys here, even in situations where we normally do not use it. So what I mean by that is normally things, for example, like zinc, or silver, or cadmium, they have sort of a fixed positive charge, which means when we name them, we usually don't use a Roman numeral, but in the context of coordination compounds and complex ions, we actually would use the Roman numeral. So we would write silver, Roman numeral 1. Also, another very weird thing that can happen with a complex ion, which doesn't sound correct what I'm about to say, but you could end up with a neutral metal that's 0. Yeah, so you could end up with a complex ion and the metal could be 0. So they will also sometimes put 0 in where the Roman numeral will go as well. So that can possibly happen. Now, if the complex anion, or if the complex ion is an anion, which basically means it's negatively charged, we use kind of the old school name for the elements, and those are the guys that end with 8. So instead of copper, we would use cuprate. Instead of iron, we would use ferrate, plumate, zincate. I could be making this stuff up. I probably am, but you would use kind of that old school name of everybody. Now, if your metal is, or your complex ion is positive, you can use just the regular old name with the Roman numeral. By the way, if you use the old school name, you still include the Roman numeral with it as well. So you use the Roman numeral no matter what. Now, when you are naming a coordination compound, the metal part of the name of the complex ion should always come at the end of the complex ion part of the name. I said a lot of stuff right there. So let me try that one more time. So the complex ion part, the metal part of that should always be the last thing that is named when you're doing the complex ion part. I'm not saying it should be at the end of the name, because it might actually come at the beginning if it's positive, or it could come out at the end of the name if it is negative. So you will basically be naming it 2 things, the complex ion, and you also be naming the counter ion. The good news on the counter ion is it's pretty much just the name of the counter ion, whatever it is. So if it's like potassium and you got 2 of them or 3 of them, you just call it potassium. Like the nitrate we just saw, if you have 3 or more of them, or however many you have of them, you just call it nitrate. So counter ions are pretty much just the name of it, whatever it may be. And then you got your complex ion. So let's take a look at some of these fun names. We got H2O, which is aqua. We have our amine. We have our carbonyl, our methylamine. Our halogens are named very much like they do in organic: fluoro, chloro, bromo, iodo, a little hydroxo, a little cyano for some cyanide. Here's some of those older school names that we were talking about. So iron is ferrate, copper is cuprate, lead there's plumate, silver is argitate, gold is urate, and stannate there for some tin. Here's some other ones. We got our hydroxo, our oxo for oxide, our carbonato, our oxalato. I feel like I'm ordering something at Starbucks here. And I'll take a double shot of oxalato with a carbonato and a nitro for our nitrite. Again, here's really the name for ethylenediamine, but as I mentioned, both in formula and in name, it's pretty much acceptable to just write the EN for both parts. If you want to write it out, you can. And this guy down here is actually the EDTA. That is a mouthful right there, I think, right? So that is ethylenediamine tetraacetate, or tetraacetic acid, sometimes referred to. That is what EDTA stands for right there. That's like the extra credit question on the exam, right? Spell EDTA. What is, how is the actual name? So let's go back to our couple of guys that we were looking at there a second ago, which are these guys here. So why don't you take a second here and give your shot here at these guys' names. Okay, let's take a look at it here. Just make sure you're on the right track. We'll do a few more before we're done. All right, so we're gonna take a look at this. So we're gonna start with the counter ion here, and basically it's just the name of it. So that would be potassium, so that's not too bad. We obviously determined later or a minute ago that our complex ion is negative, which means in this case, we do need to roll with gold's non-official name, which is the one that ends with the 8. So we will be using urate in this case because our complex ion is negative. So that would be what we would want to use for gold. Come back here. So we know we have urate, and we do know we figured out earlier that it was a Roman numeral 3. We do have 4 of our hydroxides, right? And again, if we go to our table, hydroxide here is hydroxo, so that's what we want to use. We also have 4 of them, which means it is tetra. So that is tetrahydroxo. And now we could put all that together. We're going to start with the counter ion in this case. This is positive. We will then roll in with our ligands, tetrahydroxo, and then we will end with the urate Roman numeral 3. So again, this is the complex ion part of the name. The metal comes at the end. This is the counter ion part of the name. That is a mouthful. Potassium tetrahydroxyl urate 3. Any questions on that one? Yeah. So whatever way, wherever you're naming the complex ion part, the metal should always come at the end of that part of the name. So in this case, this is what I was trying to mumble through earlier. In this case, the complex ion is negative, so the complex ion part comes at the end. So at the end of the name here, we do want to end with the metal. Now that's different than what we're going to see here on the guy on the right. Our complex ion part actually comes first. So still at the end of the complex ion part of the name, we want to have the metal part of it there before, in this case, we go to the counter ion for the guy on the right. So let's take a look at this. So in this case, our complex ion is positive because it comes first. Our counter ion here is negative, as we determined earlier. So that means a couple of things. We are going to get our ligand here, which is 6. So 6 is hexa. And again, NH3, which is ammonia, we will again use the proper sort of name for it, which is right here, amine. So we will put that in there. So we got hexa, amine. And we already determined that the chromium here has a +3 charge, and we will use the regular name here. of chromium with a Roman numeral 3. So now that is really our complex ion part. So we're ready to name our last part, which is our counter ion, which is nitrate. Again, it doesn't matter how many you have, it's just going to be called nitrate. So putting our complex ion part of the name together, we once again want to start with the ligands. So that'd be hexaamine. And this is what I was talking about at the last part of our complex ion part of the name. It would be our metal. And then we would have our counter ion in this case. So this would be hexaamine, chromium 3. And then once again, this is the complex ion part where the metal comes at the end of the name of that part of it. And we end up with nitrate in this case. Any questions on that there? Yeah. You use the regular elemental name if the complex ion is positive. If the complex ion part of the coordination guy is negative, then you got to use kind of the old school name, which will end in 8. What's that? It could. It could. Any of them could end up there, and it would just be chromate. Yeah. Chromate. Yeah. So kind of. Some of them are a little weird, because they go with the kind of historical names, like plumate for lead and stuff like that. But some of them you could kind of almost figure out by just adding ATE to kind of the end of the name, like zincate and stuff like that. But you would kind of roll with kind of the older school name. Like iron obviously comes from ferric, ferros, and ferrate. So that's where that's kind of older certain name for iron comes from, which is why it's Fe for iron, right? Now, if we had, by the way, just the complex ion part by itself, so earlier we had basically this guy here. If we wanted to give the name of just this guy, it pretty much is just this part. And you typically would put ion at the end of it. Yeah. So that would be the tetrahydroxyurate 3 ion. If you had just the complex ion part by itself, you pretty much just drop out the counter ion part of the name when you would do it. Any questions on that there? All right, let's try a few more here. Fun with naming continues. All right, why don't you try this one here? Okay, let's take a look. So once again, just really from the setup here, we can see that this should be our complex ion. This would be our counter ion. And we know really from the setup here that our complex ion is negative because it comes second. Our counter ion is positive because it comes first. We probably want to figure out the oxidation state of our chromium there. So C2O4 is oxalate, which has a -2 charge. There's 3 of them, which means there's a -6. Coming out to our counter ion is +1 for potassium. There's 3 of them, which means it's +3. That means here the chromium is rolling with a +3 charge. Yeah. Questions on that there? So what that also means is, again, our complex ion here is negatively charged. So we are going to go with the older way of naming our metal, which means we have a little chromate Roman numeral 3 in this case. We also have 3 of our oxalates, which, as we can see from the previous page here, oxalate is oxalato. So we got a little oxalato happening there. And there's 3 of them, which is trioxalato. Now, I will say some people for oxalate, because it's sort of bidentate, they will also use tris as well for it. So we got that, we got our counter ion. So we could roll with potassium. And then we would go with trioxalato and our chromate Roman numeral 3. Once again, this being our complex ion part, our metal coming at the end of that part of the name. Any questions on that one? The other name again would be potassium trisoxalato chromate, Roman numeral 3. So oxalate, it's like the only one that people kind of use that one both ways as well. By the way, the coordination number for this guy would be, coordination number is 6. So this is one of those bidentate ones, which means for every oxalate that you have, it could bind in 2 places through the 2 oxygens. So everyone gets you 2. So 2 times 3 would be actually 6 here for the coordination number. So this is what I was saying earlier. Sometimes people fall into the habit of it's always that number there, which it is if it is monodentate. But if it's not monodentate, it's bidentate or polydentate, then it will be a different number based on what it is. Any questions on that there? Yeah. Yeah, so basically what you have going on here, if you drew this, is you have chromium for the complex ion part, kind of in the center. And then you basically have 3 of these oxalates kind of hanging out. And we'll just draw it like this here. Drawing upside down. There you go, I'll go that way. And it's basically these single bonded oxygens that will bind in. That's your complex ion part. And that's why, again, here, when we look at it, our coordination number is 1, 2, 3, 4, 5, and 6. Each of the oxalates basically will supply 2 bonding or 2 atoms that are donating electrons to that metal. And obviously you got 3 potassiums floating around in there as well. Yeah. Any questions on that there? Yeah. Okay, let's try a couple more here. All right, so top one, let's go name, and bottom one, let's go with the formula. And here's another list of some more of the kind of older school names. As you can see, nickelate, manganate, tungstate. Okay, let's take a look at these here, see how we're doing. So once again, here we can see our complex ion part comes first. So we do know it's positive, which means we can use the regular name there for the metal. This would obviously be our counter ion that comes negatively last. Looking here for water, that's a 0 in terms of its charge. Chloride here is a -1, and there's 2 of them. Gives you a -2. We also have a second chloride on the outside, which is -1. And again, to get this to 0, that means that the oxidation state on our chromium is +3. There won't always be +3. It seems like we ran into a lot of +3 so far, but in this case, it is +3. We got a couple of different ligands here. We got 4 waters, so that is going to be tetra aqua or aqua, depending on whichever way you like to do it there, A or O at the end. And then we have 2 of the chlorines. So that would be a dichloral situation. And we have our chromium that we're going to use the whole name and a Roman numeral 3. And then our counter ion would be just chloride. So putting this together, we want to go alphabetical. So alphabetical means which one goes first? It does, because alphabetical, we're looking at the A versus the C, so not looking at prefixes here. So even though the prefix isn't alphabetical, we are looking at the ligands here. So the tetra aqua would come first. So this would be tetra aqua dichloral chromium 3. Good thing I got a little bit of room left, and then chloride here, right? That's not a mouthful. I don't know what it is. There it is. Tetra dichloral chromium 3 chloride. If we had just the ion by itself, it would be tetra dichloral chromium 3 ion, basically. Any questions on that name there? Bless you. Here we're going to write the formula. So we're just going to dissect what we got going on here. This part here is the complex ion part. And you may ask, how do I know that's the complex ion part? Because I see the metal here at the end of that name, right? So we know that the metal always comes at the end of the complex ion part. That means anything before the metal should be part of the complex ion. Tris ethyl endyl diamine is basically, I have 3 of these guys here. If you want to write out the formula, you can, or you can just use the EN. And I do have a cobalt that is a +3 charge. So basically, I'm going to put those guys together to make my complex ion. And what would the charge be on my complex ion at this point? It would be +3, as EN is 0. That's important because I'm going to, in this case, that's actually a 2, huh? I should actually look at the Roman numeral better. There you go. It's not too bad. It's kind of like a 3, but 1 less. All right. There we go. That's a 2. That's how you know you're getting old. You can't even see it in front of you. All right. So that means that whole thing has a +2 charge. And once again, that's important because our counter ion, which would be here, we know is sulfate, which is SO4 2-. That means we really just need 1 of those guys, right, to balance that out. So we will put that together, get rid of the charge, and that means that we just need 1 sulfate there. Will look something like that. Yeah. Any questions on that there? All right, so when you're putting it together, it's kind of important to figure out, what the overall charge is on your complex ion, so you can obviously balance it out with the proper number of counter ions. Let's do a few more here for fun. Couple names on these guys here. And I'm not sure if the brackets and stuff are correct on yours or not, but fix them if they're a little bit different than what's up here. By the way, coordination number on these 2 guys here before we continue on. Coordination number on top guy is, coordination number would be, we have 4 and 2, which would be 6 in this case, yeah, for that guy. What's the coordination number on this guy? EN is bidentate, which means coordination number here would also be 6 as well. So that was a nitrogen one I drew earlier where the 2 nitrogens could attach. So it's very much like oxalate. So both of these guys would have a coordination number 6, basically. All right, back to these. Complex ion coming first, and then we know it's going to be positive, which tells us in terms of the naming, we could use the regular name of the metal. Obviously, our counter ion in this case is going to be negative. So we will first, probably good place to start again is our oxidation state on our metal there in our complex ion. NH3 is 0. Chloride there is -1 and -1, but there's 2 of them. So that's a -2. So here we do hit a cobalt that is +3. So we know we have a cobalt Roman numeral 3 happening. We got 5 of our ammonias. So 5 is penta and amine. And we also have a 1 chlorine, which would be chloral. And putting that in alphabetical order actually is what I just did there. They would go in that order. So that would be pentaamine, chloral, cobalt 3. And then our Cl, which is our counter ion, would be chloride. So that would be pentaamine, chloral, cobalt 3, chloride. Any question? Yeah. Question? You wouldn't, although I kind of scribbled over a lot of it there. Let me erase some of that. The Cl2 here, which you're talking about, I believe, is this guy here, right? And that's on the outside, so it's actually the counter ion. So we name counter ions pretty much regardless of how many there are. We just basically just call whatever the name would be. In this case, it would take chloride because it is negative. So it would be sort of equivalent to if you were thinking just like in a basic ionic compound. If you had CaCl2, you would call that calcium chloride. So it's the same idea as that. Yeah, so even though there's 2, but if there was a 2 for this guy inside where the complex ion part is, then you would need to use a prefix for it. Other questions? Coordination number on this guy here would be 6. We got 5 NH3s and 1 Cl, and those guys are directly attached to the cobalt, which would be in the middle in this particular case. Coming to our next one here, we see our complex ion is actually going to be negative in this case. Our counter ion is going to be positive. So that means we need to go kind of with the older name there for iron, which is ferrate. The charge on the iron, Cn is -1. There's 6 of them. It's -6. There are +1 for our potassium and 3 of them. So +3 and -6 means that the iron here will also be a +3. So we got a little ferrate 3 happening there. We also have our Cn-, which is right there, cyano in terms of its name. So we'll put that in there. So we have hexacyano. And we will start here now with the counter ion because it's positive. And even though there's more than one, it will just be potassium. Next comes our ligand, which will be hexacyano, followed by our metal at the end of the name, ferrate 3. Questions on that one there? And once again, if you had just a complex ion in this part, it would be hexacyano ferrate 3 ion, basically. All right. Last 2 here. Let's do some formulas. We're looking for the formula for triamine bromoplatinum 2 chloride and potassium hexafluoral cobaltate 3. Okay, let's take a look here. So we just want to really pull out the parts from the name. It's a good way to do it. So we'll just start here with triamine. So that means I basically got 3 NH3s. Bromo means I have a Br. And platinum 2 means I got a PT +2. That's really my complex ion part, right? Because all that comes before the metal part of the name. So I could pop that into a box here, basically. And we could do something like this. Also a good idea to figure out the charge here on this. So that is +2, that's 0, that's -1. Excuse me. Which means our complex ion is a +1 charge. That means we just need 1 Cl to balance it out. So we will go with 1 Cl there, kind of clean up everything else. And there we go. Cl. Any questions on that there? Same thing with the second one. We have our counter ion first, which is potassium. We then have 6 fluorines. and a cobalt that has a +3 charge, which is our complex ion part here. So putting that together, this is +3. That is -1, and there's 6 of them, which means this guy here actually has a -3 charge overall. That means we need 3 of those guys to balance it out. So that would give us K3COF6 as our formula here. Any questions on that there? Question on how to name complex ions, coordination compounds, oxidation numbers, coordination numbers. You need to be able to do all that stuff, yeah? All right, we will, I think, lay it up there, yes. I can. What are the coordination numbers for this one? This one would be, that is a lot of numbers. Yes, that is 3, and one more makes 4 here. Again, basically in this case, you have a platinum and you got 3 NH3s attached to it and a bromine basically attached to it, which would be 4. Each of the nitrogens are the only things that attach from the NH3, so that's 3, and then one more there makes 4. Coordination number here would be 6, and that is from a cobalt in the middle with basically 6 attached there, yeah. And here, coordination number was 6. We did that one there, and then 6 on that guy as well for the CN. Other questions? All right, we will then wrap it up